In this presentation, I am going to explain the previous GATE questions and answers for the year 2021, and the topic covered is electrical machines. Now let us see 2021 GATE question that carry 2 marks. In a single phase transformer, the total iron loss is 2500 watts at nominal voltage of 440 volt and frequency 50 Hz. The total iron loss is 850 watts at 220 volt and 25 Hz. Then at nominal voltage and frequency, that is 440 volts and 50 Hz, the hysteresis loss and eddy current loss respectively are, options are option A 1600 watts and 900 watts, option B 900 watts and 1600 watts, and option C 250 watts and 600 watts, and option D 600 watts and 250 watts. Now coming to the problem, iron loss of the transformer at nominal voltage 440 volt and 50 Hz. Iron loss means that includes hysteresis loss and eddy current loss. Therefore, the iron loss of the transformer at 440 volt and 50 Hz, that is given as 2500 watts. And if you see the V by F, that is voltage equal to 440 volt and frequency equal to 50. For the ratio V by F, that ratio is equal to 440 divided by 50, V is equal to 8.8, corresponding to the nominal voltage and frequency. Now corresponding to the voltage 220 volt and 25 Hz, that is the corresponding iron loss is equal to, or the sum of hysteresis and eddy current loss equal to 850 watts. Therefore, for the iron loss of the transformer at 220 volt and 25 Hz equal to 850 watts, and corresponding to this case, V by F ratio equal to 220 divided by 25 equal to 8.8. That means that in both cases the ratio V by F is a constant, that is, or same, that's a constant, same as 8.8. That indicates that the ratio V by F indicates the flux, or V by F is same means that flux is same, or the flux density is same in both cases. That flux density in the core flux density is same when in the voltage for 40 volt and 50 Hz, as well as 20 volts and 25 Hz. Now continuing the same problem, here as we know that the iron loss consists of eddy current loss and hysteresis loss. Eddy current loss, that is PE, that is equal to the constant KE into B max square F square T square V. Maximum flux density and F frequency, T is the thickness of the lamination, and V is the volume. Or we can see that one in this case, Ke is a constant, Bm is a constant, of course T is also constant, and volume is also constant. Or we can take it that is equal to a constant. I am putting it as K1 into F square, or eddy current loss is equal to the constant K1 into F square, that I am marking at first equation. Similarly, hysteresis loss equal to the equation PH equal to eta, that is, that's called Steinmetz constant, eta Bmax to the power of 1.6 into F into V. Here also eta constant, Bmax is a constant, V is also, volume is also constant. Therefore, we can say that when the hysteresis loss is equal to a constant, another constant K2 into F. Therefore, these are the two equations. Eddy current loss is proposed equal to K1 into F square, and hysteresis loss is equal to K2 into F. Therefore, the total iron loss is the summation of the eddy current loss and hysteresis loss, which is equal to K1 F square plus K2F. Therefore, the iron loss equal to K1 F square plus K2F. Or now coming to the values that is given, that is 2500 is the iron loss corresponding to 50 Hz and of course 440 volt. Therefore, substituting in this equation, what we get as 2500 equal to K1 into frequency is equal to 50 Hz. Therefore, 50 square plus K2 into 50. Therefore, this equation equal to, we can see that one, 2500 K1 plus 50 K2 equal to 2500. Therefore, this mark it as the equation 4. Similarly, the second case, that is when the voltage is reduced to 220 volt and frequency equal to 25 hertz. Corresponding hysteresis and eddy current loss summation or iron loss is equal to 850. For 850 equal to K1 into F square minus 25 square plus K2 into 25, or that reduces to 625 K1 plus 25 K2 equal to 850. Therefore, this equation 5. We have to solve this equation 4 and 5, and you have to find out what is the constant K1 and K2. Solving 4 and 5, we will be getting K1 equal to 0.64 and K2 equal to 18. Therefore, the equation now it becomes the iron loss equal to, which is equal to the eddy current loss plus hysteresis loss, which is equal to K1. We have to substitute that K1, which is equal to 0.64 F square plus 18 F. Therefore, now you have to find out what is the hysteresis loss corresponding to the, as well as eddy current loss corresponding to the nominal frequency, that is 50 hertz. For that one, we have to substitute the corresponding values of K1 and K2, K1 and K2 here. Therefore, corresponding to that one, this is the eddy current loss, that is equal to K1 into F square. K1 is given as 0.64. Therefore, the eddy current loss is equal to K1 into F square, or 0.64 into 2500, it is equal to 1600 watts. Hysteresis loss equal to K2 into F. K2 equal to 18. Therefore, that is equal to 18 into 50, or that's equal to 900 watts. Therefore, the option here, it is equal to the option B, which is equal to the hysteresis loss equal to 900 watts and the eddy current loss equal to 1600 watts. Therefore, the answer is option B. Now let us see another problem, 2021 gate question that carries 1 mark. Consider that table given. There are 3 columns in which the first column represents the constructional features, second column the machine type, and third column is the mitigation. So the first column we have the damper winding, that is the constructional features. Damper winding is the skewed rotor slots is the, and compensating winding is the, that is marked as PQR. And the machine type, it is marked as induction motor, that is S, transformer T, synchronous machine U, and DC machine V. Similarly, what is mitigating by this one is given as hunting, that is represented by X, and magnetic locking, that is noted as Y, and armature reaction, that is indicated as Z. Therefore, we have to match this column, the element in the column 1, 2, and 3. Therefore, that is the correct combination that relates the features, the first column, the machine type, second column, and the mitigation, third column. That is the correct combination is that. What is that? That is the question. Therefore, that is given as option A, it is given as PVX, that is P damper bars, V, that is the DC machine, X hunting. Similarly, second one QUZ. Q means skewed rotor slots, and U means synchronous machine, and Z is equal to armature reaction. Like that, the third one is RTY. That is R means compensating winding and transformer, and Y is the magnetic locking. That is not correct answer. The option, will be explaining that later in the coming slide. The correct answer is option B. Option B means that PUX, that is P means damper bars, U means that is used in synchronous machine, and the purpose is that to eliminate the hunting. That is why PUX, that's the correct option. PUX. Second one, it is equal to QSY, skewed rotor conductor, that is used in induction machines, that is one, and that is Y, magnetic locking. To avoid the magnetic locking, that is used. That is QSY. And next one, RVZ, compensating winding, is used in DC machine for the armature reaction. Therefore, that is the third correct option. Therefore, the answer is option B. Now, continuing the same problem, that is, as I again am explaining, the damper winding. The damper winding or the damper bars damper bars are used in synchronous machine to eliminate the hunting. Damper bars are used in synchronous machine to eliminate hunting. Second one, skewed rotor slots, that is skewed rotor slots are used in induction machine to reduce the magnetic locking. That is called cogging, to avoid the cogging. Therefore, that is the second one. And the third one is that the compensating winding is used in the DC machine to neutralize the armature reaction. Therefore, RVZ. Therefore, the correct option, as I already told in the previous slide, it is equal to the option B. Therefore, this is the correct option. Now let us see another problem, that is 2021 gate questions that carry 2 marks. An 8-pole 50 Hz 3-phase slip-ring induction motor has an effective rotor resistance of 0.08 ohms per phase. Its speed at maximum torque is 650 rpm. The additional resistance per phase that must be inserted in rotor to achieve the maximum torque at the starting is how much? That is the question. Round off to 2 decimal places. Therefore, neglect the magnetizing current and the stator leakage impedance. Consider the equivalent circuit of parameters referred to the stator. Therefore, that is carries 2 marks. Therefore, this is the torque slip characteristics of that one. This is the induction motor torque slip characteristics. When the rotor resistance, that is effective rotor resistance, equal to 0.08. Therefore, this is the maximum torque is this one, and the slip corresponding to maximum torque is represented as SM. That slip corresponding to the maximum torque, that is the maximum torque, this one, that is corresponding to that one is equal to SM. Actually, that SM and the rotor is, rotor resistance are related by R2 equal to SM into X. We'll see how does it do. Therefore, coming to this one, let us see first synchronous speed of the motor. Synchronous speed equal to 120 F by P. Ns equal to 120 F by P. 120 into 50 divided by 8, 750 rpm. Therefore, the speed of the motor, that is equal to 650 corresponding to the maximum torque. Meaning that corresponding to the maximum torque, the rotor speed equal to 650 and the corresponding slip equal to 750 minus 650 divided by 750, or that is equal to 0.133. Therefore, this is the slip. That is called the slip corresponding to the maximum torque, S sub. And to that one, we are getting the maximum torque. Therefore, that is first we will be finding out what is the slip corresponding to the maximum torque. That is calculated as 0.133. Now, continuing the same problem, this is a torque slip characteristics, and this is why we found out then corresponding to the maximum torque, the slip equal to Sm, which is equal to 0.133. Now, the corresponding to that, the relation is that at maximum torque, the corresponding relation is that rotor resistance R2 equal to Sx2. Corresponding to the maximum torque, the rotor resistance R2 equal to Sx2. S means the slip corresponding to the maximum torque, Sm into x2. From this equation, we can find out what is the reactance x2, which is equal to R2 divided by Sm, 0.08 divided by 0.133. Therefore, the x2 equal to 0.08 divided by 0.133. This is the rotor reactance. In this case, we can see that one. Now, we are introducing a resistance, or we are adding a resistance in series to the rotor so as to get the same maximum torque at the starting. When slip equal to unity, that is starting, we have to get the same torque. Then what should be the additional resistance to be added into series to the rotor? That is the question. Therefore, to get maximum torque at the starting, that is starting means slip equal to unity. Therefore, in that case, this summation of this resistance, rotor resistance R2 plus the external resistance that we are adding, that should be equal to Sx2, but in this case, S equal to unity, that should be equal to X2. X2 we already calculated 0.08 divided by 0.133. Therefore, here, substituting in this equation, we can get that R2 equal to already given as 0.08. For 0.08 plus external resistance that is to be added plus Re, that should be equal to X2. X2 equal to 0.08 divided by 0.133. Therefore, substituting this equation, we can get the additional rotor resistance to be added, that is Re, it is equal to 0.08 divided by 0.133, that minus 0.08, or we will get 0.52 ohms. This is the Re value that is to be added in series to the rotor, so that we will be getting the same torque, that is the maximum torque at the starting when slip equal to unity. Therefore the answer is the additional resistance to be added equal to 0.52 ohm. Let us see another problem, 2021 gate question that carries 1 mark. The power input to a 500 volts 50 hertz 6 pole 3 phase induction motor running at 975 rpm is 40 kilowatt. That is the power input to the motor, that is marked as a block diagram here. This is power input equal to 40 kilowatt. The stator losses are 1 kW. Therefore, the stator, copper and core loss, that is equal to 1 kW. If the total friction and windage losses are 2000 or it is equal to 2.025 kilowatt or 2025 watts, that is the total friction and windage loss. Then what is the efficiency? That is the question. Now let us see the power flow diagram of the induction motor. For the electrical power input, that is marked as it is equal to PI. That is given in the problem as it is equal to 40 kW. That is, it is called 40 kW or it is equal to 40,000 watts. That is the electrical input to the motor. And from this one, the stator copper and core loss, no, that is given in the one, it is equal to 1 kW. Therefore, that is to be subtracted from this one. The remaining thing is the power that is transferred from the stator into the rotor. That is also called air gap power. The air gap power is this one, and that is transferred to the rotor, and PAG, and the mechanical power output is equal to, actually it is equal to 1 minus S times PAG. We have to find out what is the slip of the motor, and 1 minus S times the air gap power is that is the power, mechanical power output of the motor. And from that one, we have to subtract what is called the friction and windage loss, that is given as 2025 watts. Then you will be getting what is the shaft power, that is the power output available, P out. So the question is that what is the ratio P out divided by P in? That is expressed in a percentage. Now coming to here, the electrical input power is equal to 40 kilowatt, means that it is equal to 40,000 watts. This is a 40,000 watts. And the rotor input power or the air gap power, you have to find out what is the air gap power. That is, we have to subtract the stator core and copper loss, stator copper and iron loss. That is to be subtracted from the input. Then remaining is available to convert, or that is transferring to the rotor, air gap power. Therefore, we are subtracting that one, that is given as 1 kilowatt. Therefore, 1000 watts is subtracted from 40,000 watts. Then you will be getting 39,000 watts is the air gap power. Now, once we calculate the air gap power PAG equal to 39,000, then we have to see what is the mechanical power developed, which is equal to 1 minus S times PAG. S is the slip. So we have to find out what is the slip. Slip me to calculate synchronous speed equal to 120 F by P, 120 into 50 divided by 6, or 1000 RPM is the synchronous speed of the motor. And the motor speed is given as 975 RPM. Therefore, you can find out what is the slip, 1000 minus 975 divided by 1000, or 0.025, or it is also 2.5 percentage, or 0.025 is the slip. Now, then we have to find out what is the mechanical power output, which is equal to the, we have to that is you can calculate, which is a mechanical power developed as such. PM is equal to 1 minus S times air gap power. That is 1 minus 0.025, air gap power equal to 39,000, which is equal to 38,025 watts. That is the mechanical power developed this one. Now from this one, we have to subtract the losses, that is friction and windage losses to be subtracted. That is given, it is equal to 2025 watts. Therefore, we have to subtract this one from this. Then we'll be getting what is the power output. Therefore, that is equal to, it is equal to this one, 38025 or 38,025 minus 2025 watts, or that is equal to 36 watts, 36,000 watts. It is equal to 36,000 watts is the power output, and input equal to 40,000 watts. Therefore, the ratio output power divided by input power, that ratio equal to 36,000 divided by 40,000 in percentage into 100, which is equal to 90%. Therefore, the efficiency corresponding to this condition of the induction motor is equal to 90%. The answer is 90%. Now let us see another problem, 2021 gate question, and that carried 2 marks. A belt-driven DC generator running at 300 RPM delivers 100 kW kilowatt to a 200 volt DC grid. It continues to run as a motor when the belt breaks, taking a 10 kW from the DC grid. Therefore, that is working as a motor. First case, it is working as a generator. The armature resistance is 0.025 ohms. The field resistance is 50 ohms. And the brush drop is equal to 2 volts. Ignoring the armature reaction, the speed of the motor, that is, when it is working as a motor, what is the speed? That is the question. That is in RPM. Round off to 2 decimal places. Therefore, in the first case, that is working as a generator, and that is delivering a power, or that is giving a power of this to the load, 100 kilowatt. And the voltage here is equal to 200 volts. Then we have to find out what is the load current. Therefore, the speed is given as shunt, it is working as a shunt generator. The speed of the generator is given 300 RPM, and the power output equal to, which is equal to 100 kilowatt, that is this much is delivering to the load, and the voltage, this low voltage equal to 200 volts. And what is the load current corresponding to this power and voltage? Load current equal to 100,000 divided by 100 into 10 raised to 3 divided by 200, which is equal to 500 amperes. Therefore, the load current is equal to, this load current is equal to 500 amperes. And we have to find out what is the generator current. Then this current, shunt field current, is equal to same voltage 200 is coming across the shunt field winding, and the resistance is equal to 50 ohm. Therefore, 200 divided by 50, which is equal to 4 amperes. Therefore, the shunt field current is equal to 4 amperes. Therefore, the total current from the generator is equal to the load current plus the shunt field current, which is equal to 500 plus 4, or 504 ampere is the total, the generator current. That is 5 that for the armature current, which is a summation of the load current as well as the shunt field current, which is equal to 500 plus 4 amperes, or it is equal to 504 amperes. Therefore, load current equal to 100,000, or that is 100 into 10 raised to 3 divided by 200, which is equal to 500 amperes. And the shunt field current, that is the shunt field current, which is equal to the voltage equal to 200 divided by 50, which is equal to 4 amperes, and we got it as armature current is equal to 504 amperes. And the brush drop is given as 2 volt. Therefore, the generated voltage is the summation of the armature resistance drop plus brush drop plus this voltage, that is the terminal voltage, and that is equal to, that voltage is equal to the line voltage plus the brush drop plus the resistance, armature resistance drop. And if you add up here, out the line voltage equal to, or the voltage that is available across the load as equal to, the VL equal load voltage, of course not line voltage, so load voltage equal to 200 plus of course the current equal to 504 amperes, 504 into 0.025 armature resistance plus brush drop equal to 2 volts, or adding up we will be getting 214.6 volts. Therefore, that is the generator voltage, and we can see that there's a relation with that. The generator voltage is proportional to the corresponding speed. I am putting that speed as N, which is equal to 300 RPM. Now continuing the same problem here, the previously we have seen it is working as a generator, shunt generator. Now we will be seeing what is in shunt motor. That is, supply is here. Suddenly the power is taken from the DC grid as such. Therefore, it is working as a motor in the second case. And when it is working as a motor, the power taken is given as 10 kilowatt. Then we can calculate what is this current. What is the current taken from the grid or DC grid? Or we can say that power taken from the DC grid equal to 10 kW, and the input voltage equal to 200 volts, same voltage as we have seen in the first case. And the load current, what is the current taken from this one, which is equal to of course it is equal to 10 kW, or 10,000 divided by 200 volts, which is equal to 50 amperes. Therefore, this current equal to 50 amperes. And of course, here the shunt field current is same as the previous case, that is equal to 200 divided by 50, or 4 amperes. For this current is equal to 50 amperes, and up here 4 amperes is flowing here. The balance current only coming into the armature. For that armature current equal to 50 amperes minus 4 amperes, which is equal to 46 amperes. That is here armature current equal to the current that is here the load current that is coming IL minus what is the shunt field current 50 minus 4, which is equal to 46 amperes, is the armature current. And due to this armature current, drop is equal to, which is equal to that much current 46 into the corresponding armature resistance 0.025, and the brush drop is same as, that is 2 volt is there. Therefore, the total voltage, if you see that one, back EMF, that's called the back EMF. When it's working as a motor, here we say back EMF. Back EMF is equal to the this voltage. What is this voltage? That is the load voltage, as or the input voltage is equal to 200 volts. For 200 minus the drop in the armature resistance and the brush drop, that is equal to 200 minus the current is equal to current armature current equal to 46 amperes. So 46 into 0.025 armature resistance plus the brush drop 2, which is equal to, we will be getting, it is equal to therefore the back EMF is given by now 200 minus the current armature current 46 amperes into 0.025 armature resistance plus 2, that is the brush drop. So this is subtracted from the 200 and we'll be getting it is equal to 196.85 volts. Therefore the corresponding speed is we have to find out, this is to be calculated, motor speed corresponding to this when it is working as a motor, what is the speed? Let us see, that is noted as N1. For this back EMF, I can say that one, this is a back EMF which we already calculated as 196.85, and that is proportional to the corresponding speed N1. Therefore, that is proportional, or we can say that 196.85 is proportional to N1. And next one, for the generator, here we see that one, the generator voltage is proportional to N, which is equal to, already we have seen, it is equal to 214.6. That is proportional to the corresponding speed equal to 300. For from these two equations, we can find out what is that equation 1 divided by 2. That is 196.85 divided by 214.6 equal to the corresponding speed that is to be found out, and it is working as a motor. N1 divided by, means generator speed equal to 300 RPM is given. Therefore, if you take that, when the unknown is the motor speed, which is equal to N1 equal to 196.85 divided by 214.6 into 300, which is equal to 275.19 RPM. Therefore, the answer is 275.19 RPM. When it is working as a motor, the corresponding speed equal to 275.19 RPM.